You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have Dr. Hasan Yilmaz. He received his PhD from the University of Twente in 2015 for his work on advanced optical imaging with scattering lenses. He's currently a postdoc at Yale University, Department of Applied Physics. And Dr. Hasan, thanks for coming. How are you doing?
Hi, thanks, Rich. Thanks for the introduction.
Yeah.
So
Tell me about your current work. What are you researching and working on now?
Currently, actually, I work on systems that scatter light very strongly. One of the examples of these systems is actually a very typical example is piece of white paper. The reason why we can see through glass, but we cannot see through paper is because of light scattering. Like the image information is distorted due to this random scattering. So currently, I am developing methods to control light scattering so that we can see through a piece of paper, as an example.
So how would you? So by controlling how light scatters, we could see through opaque objects that we can't see through right now?
Yes.
How would that be possible? What would be the mechanism for something like that to work?
The way that it works is actually it only works for specific type of light. For example, a laser light. So if we send a laser light through the scattering materials, such as piece of paper or white paint, what happens is light randomly follows a path inside this system. So, but even though this path looks like random, it's not random, it's deterministic. It's just too complicated. So what we can do is we can use a specific device that we call spatial light modulator, which we can control the shape of light in space. So we can measure the little amount of light that passing through this system. So we can just write a specific wavefront on this light pattern, like a specific image, such that the light can be focused through this scattering medium. So after focusing, we can scan this focus and construct an image, or directly send an image information.
So this would allow you to see through objects that normally can't be seen through?
Yes, exactly. But of course, it has limitations. Currently, we can only do this practically through like a few millimeter thick samples. So it cannot be done through very thick walls, for instance. But this is only a technological limitation. In order to control it through very thick materials, you need a very large number of pixels, maybe million to billion number of pixels, which is not currently possible.
Okay, so what would be some of the applications of doing this?
One of the applications is actually that people are working on. I'm not working on immediate applications currently, but there are other groups in Caltech, for example, Chanwayang, the group of Chanwayang, or there are other groups also in Paris. What they do is actually one application is imaging through scattering mediums such as biological tissue. Like biological tissue, like our tissue is also opaque. The reason is, again, light scattering. That's why we cannot use optical light fields, like visible light, to see inside our body. We can currently only use X-ray because X-ray doesn't scatter, but X-ray doesn't give us too much information. So currently there are groups that working on imaging deep inside scattering tissue using this kind of methods. That's one example of applications.
So where would you put the device to collimate the light? You put it right before the material, like right on top of it, or do you need also a receiving panel behind the object to interpret the light that's coming out of it?
Exactly, that's a very good question. So the idea is, in principle, if we want to image like inside my body, if there's not enough light passing through my whole let's say, full body, one of the ways is to look at reflected light. For example, we can label some target molecules or target tissue with some sort of fluorescent dye. So what we can do is we can optimize to enhance this amount of fluorescence that coming from this particular place by shaping the wavefront of light. So in this case, we will send light on the material and look at the reflected light at different color.
Okay, interesting. How close is this to being used? Has it been tested in the lab, and what kind of things can be seen?
Currently, actually, this is still not there's no method that can be applied in clinical studies. Still, it's an ongoing research. There are on one hand, there are groups for example, me. I am mostly working on physical properties of this light, understanding how light propagates through these scattering systems. But there are other groups who are trying to develop new techniques, microscopy techniques. And for example, usually what they do is they can do imaging inside brain tissue, because brain is also a scattering medium. They can, for example, specifically focus on certain positions in brain, like certain neurons. And another application, which is also closely related to imaging, is optogenetics. In optogenetics, what you do is you have a genetically modified animal, and this animal's brain cell can respond to light field. So you can basically control the behavior of animal by stimulating certain neurons with light. And the problem is, again, light scattering here, because you cannot address certain specific parts of the brain. But using this kind of methods, some groups are already can focus at specific areas of the brain to basically change the behavior of animal in a different way. That's one of the applications that people do. But this is not what I do. What I do is actually I am just trying to understand what happens, how light propagates when we do wavefront shaping.
Can you control the penetration depth of the light?
Yes.
And would that have any particular use?
Yes, I can do that. For example, there is already a theory that is developed way back in a couple of decades in very different community, condensed matter physics community. There, what they study is actually how electrons transport through a copper wire. So electrons are also waves, can be considered as waves from quantum mechanics. We know that. So what they find is there are some specific solutions of these electron waves, like specific shapes, of which that the material behaves like a superconductor. So it just basically the resistance becomes zero. So which means all of the electrical current just transports through this system. So we apply same theory to optical waves, because the light is also optical waves. So it also scatters through this random system. So which means there are specific wave solutions, like shapes of wave, that all of the light can propagate through the material independent of its thickness. So essentially, this is what I'm working on. What we can do is we can enhance the light transmittance by a couple of 2 times, 3 times, depending on the thickness. So which means we can make a reflecting material completely transparent almost. So the advantage of this is, for example, if you want to do imaging very deep inside the scattering tissue, first thing you need is light. You want light to be there. Otherwise, you cannot image anything. So this is the first step of imaging, deep tissue imaging.
So depending on the wavelengths of light, you can have them pass through someone's entire body or pass through a certain depth?
Yes, theoretically it's possible under the condition that there is no absorption. So if there is only scattering, if you find a particular wavelength, which is usually near infrared, usually our body does not absorb near infrared much, so it only scatters. In principle, if you have a lot of degrees of freedom, which means you can give a very complicated pattern to the wavefront, it's theoretically possible to find such a wavefront that all of it can propagate. But this is right now experimentally not possible. But we can see that in our numerical simulations. We also know the theory that it works.
Okay. So what are you specifically trying to learn about how light moves within an object and how it scatters?
For example, one thing that we recently discovered, it was a discovery because it was like a physical effect. As I said, there are specific solutions which we call them open channels. So all of the light can propagate. What we find out is, for example, if you have a light, like a flashlight in a very foggy day, the light that emitted from this flashlight will spread due to fog. It will spread more than ever. So it will behave like diffusing in the system, diffusion. So we know that typically in scattering systems, like diffuses, it laterally spread. What we find is actually in a system where its width is very large, and it's like a thick layer of paint, you can imagine. It's very wide width. It is thick, but its width is much larger than its thickness. What we find out that if we send this open channel, which totally transmits through the system, this light doesn't spread. It just goes straight as if there is no scattering in the transverse direction. So you can imagine it as if like light is propagating through an optical fiber. So that
how do you
was
find
pretty
an open
interesting.
channel though in a complex structure like,
yes,
let's say, the human body? Is there such a thing as an open channel? How could you find that?
How we define it? First, we measure the transmission metrics of the system. So what I mean by transmission metrics, you choose a certain set of input vectors, which can be, for example, different angles. You send light at different angles, but a lot of angles, like thousands to 10,000s of angles. And then you measure the transmitted light field behind. You can also measure the reflected, but we are measuring the transmitted. Then you can find such a matrix that this matrix has all the information that if you send a certain specific light at the input, you can predict the light at the output, basically. So this matrix gives you the whole information about input and output of light fields. So this is a kind of matrix. So which means, for example, if we want a specific output on the other side, we know what to send from the input.
Okay. But again, to find a channel through a material, does it have to be a homogeneous material or a very structured material like a crystal? Or can it be, something that's amorphous?
It can be anything. It can be like amorphous, like, for example, opaque systems are amorphous, we know. That's what we study, actually. We particularly study complex systems. It can be any type of material that you can imagine. This is very general, but as long as the light field behaves linear, what I mean by linear is, let's say I send an input field 1, and I get an input field of 2, output field of 2, and I send another input field of 3, and I get an output field of 4. When I add 1 and 3, I should get 1 and 3, 2 and 4, 2 plus 4. So which means I can add these input fields. So as long as this applies, it will always work, which means this will work for biological materials, opaque materials, glass or opaque glass, or any, even very dark materials, as long as there's some light propagating.
Interesting. So what are some of the stumbling blocks before this could be used?
One of the things is this is a very large amount of information, as you can imagine. Like, it's a big matrix you measure, so it takes time to do this measurement. Currently, for example, the device that I'm using is a liquid crystal spatial light modulator, which is actually not so different than the LCD screen you have in our daily lives, like in many devices. And this kind of measurement for 2,000 input of the matrix, it takes about half an hour. But there are other types of devices, like digital micromirror devices. They are called DMD in short, and they are a lot faster. It's like composed of very tiny mirrors, of millions of mirrors, so you can just control their angle. With these devices, you can do this measurement sub-seconds. And there are also new type of devices being developed, which is targeting for sub-milliseconds, which is especially very necessary for doing this through brain tissue, because we know that brain tissue changes very fast. So you need to do this measurement before the brain tissue changes. This is one of the challenge, like measurement speed, but it will be overcome in time. I'm pretty sure. I would say this is the main challenge now, and also number of pixels. So we will need a lot of. Right now we can address to 5 million to 1 million to 5 million pixels. So in future, it will be better if we can have like 10 million, 100 million. but this is currently not possible.
So what is so what are some of the uses of this that you envision, and when do you think that it would be commercially available?
Spatial light modulators already has been used for different purposes. Like, for example, one name is adaptive optics. So, for example, there are already microscope being developed to, for example, correct for aberrations in an image, distortion in an image, which is kind of low order correction. This kind of imaging through scattering medium, I think it will still take a while before it becomes commercial, because the main reason is biological. You cannot classify biological tissue as one type of material. Like, it's not a one layer of white paint. It's much more complicated. So, which means we still need to understand more about the structures other than the technique.
Okay. Well, what's your estimation? How long is it going to take so we can go through simple structures? You said biological, imaging through biological structures will take quite a while, but going through more simple structures, when do you think that will be possible, or is it possible now?
Actually, in principle, it's already possible to image very simple structures, but there is no market for it. There's no big market that, the problem is there's not enough number of customers that for this purpose. So that's why if we want to do this, to use this device for brain imaging, like a kind of some different version of tomography in the optical regime, I think this will take still 1 or 2 decades at least until we see something really useful.
Oh wow, 1 or 2 decades. Jeez.
Because there are a lot of problems. Like, there are a lot of not only technological problems, but still there are some scientific questions to be addressed.
Okay. Yeah. What is the best way for listeners to read papers that you put out, or to get in contact with you, or to find out more?
The best way to learn all these things, you mean?
Yes, for people to learn more, maybe to contact you.
I would say it's even though these seem like a bit advanced topic, all the bases are actually in studying electromagnetic theory. If, for example, people understand how electromagnetic waves behave in different environments, like just basic electromagnetics, together with wave physics, it's pretty straightforward to learn all this topic. In terms of experiments, like experimental techniques, I think it's mostly the way to learn it is experience, to do experiments, to work in the lab. I would say that's the easiest way.
Okay. All right. Very good. Well, Hasan, thank you for coming on the podcast. I appreciate it.
Thank you.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.